Okay.
Later on is Wednesday.
Okay. Thank you. Thank you very much. Thank you. So the next speaker is
viscous stress and elastic stress due to the nature of this particle, plus these active stresses as to incorporate some sense phenomenology. So the name of the game here is to integrate this equation of motions into the solenoid equation and try to see what's going on when we change the activity parameters to the other parameters. We have done that in a very simple geometry, which is one of the simplest non-trivial geometry that we have considered, which is a channel, which is infinite along one direction, that's the x direction, and there's finite thickness along the other direction. And we have two dynamic fields. One is the polarization angle, so the angle with respect to the x direction. The other one is the concentration of these active particles. The total density of the system is equal to the density of the active particles plus this order is conserved, so the system is incompressible. We have considered this film anchored to a non-splitting substrate here, to a wall, and then bound to a free surface on the other wall. That means that here particles are forced to be parallel to the wall, but nonetheless they can flow freely. So what we observe here is that for both polar and apolar particles, there is a transition from a regime where these particles are parallel to the wall and the system is perfectly stationary, to another state in which you have a non-uniform polarization across this channel. So these particles are actually filled from the inside. And the entire system is flowing here with some velocity. And this spontaneous flow transition, it was discovered by Janine Prost back in 2005, is actually a signature, very clear, of all these models that somehow contains liquid crystallinity and depth. So it's a very important feature. In addition to that, polar particles also exhibit a non-uniform concentration across the channel. So the concentration is actually larger when the velocity is smaller and vice versa. And this is a feature that is peculiar of polar systems, something that we don't have from the Oscillatory Flow in matter system. So what's the origin of this? What's the origin of these mechanisms? Well, because of the geometry that we have chosen, everything is translational invariant along the x-axis. And since the system is isolated, there is no applied shear, then the transverse component of the total stress has to be zero. So if you switch off the activity all of a sudden, then these stress bands can be kept by having a zero elastic stress and therefore a zero viscous stress. So with particles parallel to the wall and stable. Nonetheless, if you switch on the activity, then the same stress bands can be get by having a non-zero elastic stress and a non-zero viscous stress. Or in other words, these active stresses that are acting internally to the system can be converted into elastic stress, therefore distortion, and viscous stress, therefore flow. Similarly, if the only source of current in the system would be due to diffusion, then in a stationary state the system would be homogeneous, right? Because that's what diffusion does. On the other hand, active currents, which are due to the fact that particles are moving in the direction of the polarization, can build up density homogeneous. And that's what somehow beyond this concentration bending that was observed apparently also in different systems. And we believe this is a pretty robust mechanism, really something many. Now, this is not the entire story, though. I mean, if you keep increasing these beta parameters that represent the velocity particles are moving in the direction of the polarization, at some point you will hit a regime in which all the dynamic fields, so the polarization angle, the concentration, and the velocity, are oscillating in time with some frequency, which at least at the onset of the oscillatory behavior is proportional to the square root of this velocity. And here is an example of the Fourier transform of this polarization angle at the center of the slab, and here you can see there is a non-zero frequency. This is a space-time plot of the concentration. So what you see is like the profile of the concentration from above as a function of space and time. This means large, this means slow. So what is happening here is that these bands of concentration are bouncing back and forth in the channel. The thing is that if you keep increasing this velocity, this active velocity of this particle, at some point you will see new frequencies appearing in the spectrum. That's an example of a system with two frequencies that are irrational between each other. And if you keep increasing, you also see other frequencies appearing, although the system never becomes turbulent. Although this mechanism kind of resembles like this cascade of like oscillation that you see at the onset of turbulence in a normal flow. Now I summarize this in the sort of phase diagram. This is the stationary phase, this is the spontaneous flow, and this is the periodic flow, instead as a function of alpha. I find interesting that these three regimes actually meet at some sort of very critical point here. And it's also interesting that you actually can go directly from the stationary phase to the periodic phase without passing through the spontaneous phase. Now, for beta equals 0, this critical value is simple enough that it's worth to write it down. We have an analytical expression for all these lines. So is proportional to viscosity, to the rotational diffusivity, and inversely proportional to the square of the separation between two plates, and 1 minus lambda, where lambda is the flow line parameter. Now, this means, for example, that if you take lambda exactly equal to 1, this transition is actually cancelled. If you take lambda larger than 1, so this is a flow line with crystals, the transition is still there, but alpha becomes negative. So that's a tensile system. So this seems to suggest that there is some sort of analogy between a contractile flow tumbling system and a tensile flow alignment system, which is actually this sort of like PT invariance that both Apart and Garrett were talking about. I wasn't aware of that, but I will tell you in a minute what's my understanding of this sort of symmetry. Now, what happens if you take the system and you shear it with a constant shear rate? That's what we are doing now. And so this is a stress versus shear rate plot for a purely analytic expansion. So we switch on the beta parameter for a flow tumbling and production system. Here you see the behavior is quite different in the sense that if I increase alpha here, the slope of this curve is decreasing, so there is a decrease in the apparent viscosity that is perceived by this shearing experiment. If I increase alpha here in the flow line regime, instead the slope is increasing, so there is an increase in the apparent viscosity. So in order to understand this a little better, it's possible to do a perturbation theory in sigma, so in the value of the stress tensor itself. The linear order is actually simple and accurate enough to predict the apparent viscosity, the final viscosity. That's the way. So eta here is the bare viscosity of the solvent. Zeta is a number that depends on beta and it goes like minus 1 over lambda. K is the wave number that is proportional to alpha to 1 minus lambda. Tan K is like the tangent function divided by its alpha. So what happens here is that for a flow alignment system, this wave number becomes imaginary, the tangent is replaced by the hyperbolic tensor part, and so the apparent viscosity is increasing relatively. Now, what I find interesting here is that for a flow tumbling system, if you keep increasing this alpha, these active stresses acting internally in the system, at some point the apparent viscosity goes to 0. And the value of alpha, when this happens, is exactly the value corresponding to the spontaneous flow transition. So what happens here? It happens that apparently, in this regime, the spontaneous flow is exactly cancelling the induced flow by the shear with a resulting drop in the apparent viscosity. Now, the problem here is that if you increase alpha again, it seems that this apparent viscosity becomes negative. So what happens here? I don't know. That's exactly where I got stuck. And we are considering the idea of shear band, for example, right? But if that's what happens, though, it means that it's very different for shear banding happening complex fluid because at large shear rate. This is something that happens apparently to shear rate, and I'm not sure what it means. Now, one more thing about this sort of like duality. At the level of perturbation theory, it's actually possible to prove that the apparent viscosity for this choice of parameter, alpha, lambda equal 1 minus epsilon, where epsilon is the positive number of smaller than 1. So for a flow tumbling system, it's actually equal to the apparent viscosity for a system with minus alpha, and lambda equal to 1 plus epsilon. So the apparent viscosity of a contractile flow tumbling system is equal to the apparent viscosity of a tensile flow alignment system. Okay, and that's actually what here it seems that everybody's talking about, and the reason is very simple. I mean, you change the direction, but you change also the direction of the flow that is coming here. That is coming out. So for small shear rate, the flow is perceived identically to the shear rate. But that's true also for just for small shear rate. That is what here.
Thank you very much. Other questions? Any questions?
Good. If I understand correctly, all of the geometries that you've looked at involved a fixed surface and a free surface, either with or without shear. Are you thinking about other geometries?
So, yeah, so I mean, you're right, and then this channel geometry actually introduces a lot of geometrical constraints. And especially for what is this oscillatory regime, that never becomes turbo. So I believe this is up to the reason. And it's actually clearly not very realistic, right? Because if you want to, if you attempt to study on a Rheology, for example, then you need to have the metrics. So yes, what we have to do is to consider a two-dimensional system in some simplified geometry, maybe with some periodic boundary condition, and see what happens.
Do you know what the effect would be if your particles were not, or your particles are all monodispersed, right? They're all the same length. What would be the effect if they were polydispersed, if they had different lengths?
That's a good question. My particles are even simpler than that because this is like a purely elastic field. So it's actually a director field which exists everywhere. If they were polydispersed, I would say my guess would be that there is like some interplay between the local order and the flow, in the sense that according to the, for example, to the aspect ratio, you would have like an isotropic phase and an ordered phase, maybe coexisting together. And perhaps this can also couple with this concentration banding thing, so the fact that you have a different concentration. So I would say do that the interplay with these three things, like amount of alignment, amount of concentration, and perhaps flow. But that's a very good question, but also very complicated to have a guess right now.
There are no further questions. So according to the schedule, we'll go into a coffee break and poster session. We're going to restrict that to 1 hour, so we'll reconvene at 10:05, and then we'll have the next